So this is OH5, the first Paranthropus boisei to be found. It's probably dated to around 1.8 million years ago. And just by looking at it initially, she named it the Nutcracker Man. So already we're thinking about diet just from this skull being found. There's already some assumptions or connections with diet. So I'm going to go through these in more detail, but here are some features of boisei that are quite distinctive. So we've got a nice robust mandible. It's quite a long ramus, this bit here, quite bulky. Got really wide zygomatic arches, so these cheekbones here. Got a pronounced sagittal crest, which is sort of on top of the skull. We'll go through that. Really large premolars, so before molars, they're getting sort of similar size to the actual molars. So that's called megadontia. And then looking at teeth a bit more, they've got really thick enamel. So I'll go through these in turn, thinking about boisei. So as I said, it's got a really robust masticatory apparatus. You can see how big the chin is, how big the jaw is, the mandible. So it's got a really tall ramus, so this bit of the mandible, this lower bit, back bit, sorry. So it's not only robust, but it's sort of vertically ascending, sort of bringing some muscles that are used for chewing back to the posterior teeth, so molars. And then it's got a really robust corpus, so the corpus is this bit. It's got a reduced wishboning effect, so if it was to be feeding on seeds, for example, so mechanically challenging food, if it's going to be loading on just one side of the mouth, it's going to create some imbalance and quite a lot of stress and strain. So to be robust, it's sort of working against that massive strain just on one side of the mouth. So it's really robust in that way. Got a really nice finite element analysis here. Really nice study. So comparing simulated strain of a chimpanzee and then boisei. So it's a bit like a heat map. You can see that the male chimpanzee has got a lot of experiencing a lot of stress and strain on these bits. So I guess the more the zygomatic arches here, it's more red, and then this is less so. So it's sort of built to counteract that hard diet. Now I've mentioned a few times about zygomatic arches. These bits here, the sort of cheekbones, those are the zygomatic arches, and that is where the temporalis muscle, in humans it's sort of originating here, and then going through those arches and connecting to part of the mandible. So I guess most fossil hominins, you're never really going to see muscle preserved. So we can make some inferences about those, how wide those arches are, and that can be indicative of the size of the muscle. So you can already see that Robustus and boisei have got really wide arches. If you take this nice sort of look down view of it, you can see how wide they are. And then early human, Homo sapien, it's a bit narrower. You can still see those gaps though, that arch. And then if we look at it in this perspective with modern humans, you can't see those at all. We obviously still have them, but they're so narrow that you can't see them in that perspective. So you could say that boisei would have had really thick muscles that are taking up that big wide space. So it's sort of relating to bite force. If you've got these really big muscles for chewing, you're going to have maybe a greater bite force, and then less so in us. And then we've got the sagittal crest, so it's going in the sagittal direction this way, and it's going over the top of the skull. It's probably most pronounced in gorillas, so male gorillas have really distinctive sagittal crests. And here, this is where the temporalis muscle is attaching or originating, and then attaching to, I guess, the mandible here. And that's the same with a robust australopith. They've got that sagittal crest, and they're bringing the muscles as well. You can see there's a slight difference in direction. They're more straight down, maybe towards these posterior teeth, and that's sort of going towards anteriorly. But it's a greater lever arm for those muscles. The greater distance of working is creating a bigger bite force as well. So we've looked at sort of the cranium. If we look specifically at teeth, they've got really big premolars. So we've got boisei at the bottom, and then an early homogeneous species at the top. And you can just see by comparing them that boisei has bigger premolars. And then we've got a nice graph here that's comparing, on the x-axis we've got the molar area, and then we've got bite force on the y. It's sort of a correlation. We've got all different fossil hominins that they've plotted. And then if we remember, it's OH5 that Mary Leakey found, and that's right at the top. So they've got a really big crown area, and then it's relating to a big bite force. So they think that bigger area is sort of spreading that load on that bigger surface area. So the stress is sort of spread it around. And then if you look at it even further, you can do analysis like this. Take a slice out of this sort of digital model, and you can see the enamel's in yellow, the dentine or the rest of it is in purple. So if you compare it to a gorilla again, gorillas have really thin enamel, boisei has really thick. So it's to do with sort of longevity, as well as if a fracture were to occur from lying down on maybe a hard seed. If the crack were to occur on the enamel dentine junction, which is just the division between those two bits of the tooth, that crack is sort of less likely to reach the surface because there's a bigger area to travel through. So we've looked at some of the anatomical features, but in sort of recent years there's been a few more techniques that they've used to study boisei's diet. So there could be something more to the Nutcracker Man's diet. So a great way to look at teeth in more detail is doing microwear analysis. So they're using SEM, so a really powerful microscope, to look at the texture of teeth, sort of the topography of that area. So if you're feeding on really hard seeds, really hard food, you're more likely to get more like pitting, like dents in the teeth. Whereas if you're shearing on tough leaves and plants, it's going to be more striated, so stripy. So they've done this for boisei, and we can see what they might have found. So interestingly, they found more striations, linking to a more plant-based diet. Its cousin robustus is showing that pitting, so it's probably feeding on seeds as well. So there's sort of already more to the story than just feeding on seeds. But important to note, with microwear, it's more likely to just, what you're seeing, the pattern you're seeing, is probably just the last thing it ate before it died. So it's not representative of all of its lifetime diet. So that is a limitation of microwear. It could be that boisei, on its last day, just decided to eat some leaves. But if we just assume, it was feeding on leaves throughout its lifetime, we can go even further and do stable isotope analysis to see what kind of vegetation it was feeding on. So we know it's plants, but what kind of plants? So there's a few photosynthetic pathways that exist in nature. So we've got C3 plants. That's sort of the pathway you learn in school. They're like trees and shrubs, whereas C4 evolved a bit later than C3, but it's sort of more arid conditions, so grassland. They're able to photosynthesize a little bit differently to conserve water better. But a long story short, C3 plants have less carbon-13, so that isotope of carbon. C4 has more. So we can look at boisei's teeth and do this analysis on it, and they've done that, and they've found more carbon-13 in boisei compared to some other hominins. So we can think about they were maybe in a more grassy environment, eating more C4 plants. So it could be feeding on seeds, it could be feeding on grass. I think just looking at boisei as it is, the sort of structural form of it, the morphology, it looks like an anatomical specialist. That's what Mary Leakey probably assumed, thinking probably purely just ate nuts. But we've seen sort of a different story. So anatomical specialists might not necessarily mean you're a dietary specialist. So that's linking to this paradox in nature, William's paradox. Because there is some kind of overlap between the features of feeding on grass and the features of feeding on seeds. If you're feeding on lots of grass, you're going to need a large temporalis muscle. It reduces fatigue when you're just continuously feeding on plants. So that's sort of a link. And then, again, thick enamel, it's great for feeding on grass as well. It sort of preserves the tooth, again, for that continuous action, longevity, basically. And we've seen all those features for feeding on seeds as well. So it could be that boisei was feeding on grass the majority of the time. It's an abundant resource. But when, sort of maybe in winter, when those resources weren't there, it was able to use this really distinctive morphology to exploit the niche of nuts and seeds that are there in these sort of hostile conditions. So that's sort of to do with fallback foods. The fallback food being, in this case, seeds and nuts. So it's ready for that hostile period of time. So fallback foods here are sort of dictating this robust anatomy. So I've quickly gone through boisei's diet, but I'm going to just go through my master's project, which was linking to boisei, but looking at particular primate and their mechanically challenging diet. So I was looking at a particular monkey, as I said, the sooty mangabey. It lives in the Ivory Coast. And what's important about this monkey is that it feeds on seeds all year round. So it's dependent on it. It's a habit of theirs to feed on seeds all year round. So it's got similar morphology to boisei, thick enamel, large premolars, robust mandible, and it needs a large gape as well. You can see it feeding on a seed there. But again, that's something significant about the sooty mangabey is that they've measured its masticatory muscles and found that it has a really low predicted bite force. So it's got a low cross-sectional area of the muscles, a low leverage of those muscles, and then if sort of thought it must have a low bite force. So they've sort of thought, how is it feeding on these seeds all the time when it can't generate the bite force to do so? So I had to sort of think about this question, how are they exploiting this niche without the bite force? So I sort of took a step back and thought about its behaviour, what have they observed in these monkeys, and then even the seed morphology itself. So with most seeds and nuts, they have an endocarp, this shell, and there's sort of a line of weakness where it sort of cracks open eventually, called the sulcus. So I thought about this fact of seeds and thought about its behaviour. Is it orientating seeds in a specific way to get around generating big bite forces? So in the University of York, I used this compression testing machine. My supervisor created these sort of 3D printed perfect replicas of the sooty mangabey's upper and lower jaw and covered it in bronze. So I stuck these pieces to the upper and lower bits of the compression testing machine, and I basically I focused on the premolar and did sort of compressions of all these different seeds. So actually I had 3 different types of seeds, but I had lots of them, and I was testing it on the sulcus, so orientated on that sulcus line. So you can see this one's on the sulcus, and then I was doing the sort of perpendicular non-sulcus. And I was testing force and energy for that to then fracture. So it's sort of fairly obvious what I found, because if we think about it, it's a line of weakness. Orientating on the sulcus, you don't need to generate big force or energy. So there's low force and energy to crack that nut, basically. So it sort of reiterated that behavioural investigation really does matter. With the sooty mangabe, it may have found a way to not have to generate really big bite force, which is energetically costly anyway, and it's able to exploit a niche which is energetically rich. I guess seeds and nuts are more energetically enriching than grasses. If you not always equal function, it does have the sort of morphology to do it, but the bite force isn't equivalent. So yeah, robust morphology doesn't always equal bite force. If they were to just find a crania of the sooty mangabe, they can guess, yeah, it's probably feeding on seeds, but there's more to it in that it hasn't got a big bite force. So I've sort of linked it back to boisei. Unfortunately, we can't observe boisei in the wild. So there may be more to it. We need to think about behavioural adaptations as well. But it's great to have sort of microwear, stabilisative analysis, and recently dental chipping in boisei. To say you don't necessarily have to take the anatomical features at face value and conclude a diet. It might not be representative of the actual the context. So that sort of concludes my talk. I've got my image references and my paper references as well. Oh yeah, thank you. So are there any questions?
I do have one.